In this video, we will talk about pairs of random variables or joint distributions. We will start by talking about the density function, little f, of random variable x and random variable y. Then we will continue with the joint cumulative distribution, that's big F, of random variable x and y. These two topics, the densities and joint cumulative distribution, are totally analogous to densities and cumulative distribution of one variable. So these should look very familiar to you. Marginal densities and independence are new, so we'll go over that. And then expectation and covariance are also new, as they have to do with how one random variable relates to another. We define a density function of two random variables, x and y, as equal to the probability that random variable x takes on a value little x, and random variable y takes on a value little y. And this is totally analogous. I'll remind you what it looked like for a single variable. So the density function is equal to the probability random variable x was equal to some value x. If you recall, for discrete functions, this density function was often literally a function. So you'd plug in a value x and it would give you the probability. If there was a limited or finite number of probabilities or values that x could take, then sometimes the density function was given to you as a table. That will be similar for joint densities. In this case, we'll either have a function f of x, y, that we can plug in x and y, and then we will be given a probability, or we might have a table where we could look that up. For continuous random variables, if you recall, we did not ask what the probability random variable x would take on a specific single value little x. And that's because in any interval of the real number line, there's an infinite number of possible values that random variable x can take. And since there's an infinite number of possible values, that means the probability x takes on any single value will be infinitesimally small. In the limit, it's actually equal to 0. So what we do instead is we ask, what's the probability random variable x has a value between a and b? And what we did for one variable, random variable x, is we integrated our density function. So in other words, we integrated or summed over all our densities between the values of a and b, and that's how we calculate the probability of a and b. So for our joint density, to calculate the probability that x is between some value a and b, and random variable y is between some value c and d, we will take a double integral. We will integrate with respect to y with the limits c and d, and we will integrate with respect to x between a and b. If you recall, there is a criteria on density functions to be a valid probability function. There are two criteria, and the first is all probabilities have to be greater than or equal to 0. So the probability that x takes on a value little x and y takes on a value little y has to be at least 0. Second, if you integrate the density over all possible values of x and y, either summing over or integrating, you will get 1. So in other words, if you look at all the possibilities, you will get 100%. The cumulative distribution, just to remind you what it looked like in one dimension. So this big F of random variable x, if we wanted to know it at some value x1, that's the probability random variable x is less than or equal to x1. And if you recall, it's kind of like going over the number line for x and summing up all the densities up to and including x1. The same idea here for the joint cumulative distribution, that's capital F, of random variable x and random variable y is equal to the probability x is less than or equal to x1, and y, random variable y, is less than or equal to y1. To calculate the probability that x is between x1 and x2 and y is between y1 and y2, we have this formula here, which has some inclusion, exclusion. We'll do some drawings and illustrate this so that it'll be more clear. But essentially, it's the cumulative distribution at x2, y2. And at this point, we're assuming x2 is greater than x1 and y2 is greater than y1, minus the cumulative distribution at x2, y1, the cumulative distribution y1, y2, plus the cumulative distribution at x1, y1. And again, we'll see an illustration of this, and this will become more clear. The marginal densities, essentially, if you have information about the two random variables x and y together, you want to tease out the information so you can get a density for just x, or maybe you want density for just y, but you want to kind of isolate one variable. And the way you do that, if you want to look at just x, you sum over all the values for y. So for the discrete case, to get f of x, the density function for random variable x, you sum over all the values for y of the density of x and y. For the continuous, it's the same, except now instead of summing, you're integrating. And we'll do some examples of this. Independence then, now that we know the marginal densities, x and y are independent, and this has the same definition as we had in chapter 1. Independent means if you know information about one variable, it gives you no information about the probability of the second variable. So x and y are independent if and only if the joint density is equal to the product of the individual densities. Last, we have expectation and covariance. If you recall, expectation is simply a weighted value. So if we have a function, h of x, so h of our random variable x, we would sum up all the possible values of our function h of random variable x, and then multiply by the probability of that value of x. So totally analogous, we have the expected value of x and y is equal to the function value of x and y. We plug in x and y into our function, and then we multiply by the density function. And continuous is analogous, except now instead of summing, you're integrating. Covariance and Pearson coefficient. Covariance is dependent on these definitions of expected value. And then Pearson coefficient, we have this formula here. And these two coefficients are about how related or not the two random variables are. So we'll have some examples, both of the calculations, and then we'll discuss how to interpret our calculations. We're ready to do some examples. Our first example will be, in an automobile plant, two tasks are performed by robots. The first entails welding two joints. The second, tightening 3 bolts. Let x denote the number of defective welds and y the number of improperly tightened bolts produced per car. Their joint densities are shown in the table below. First, show the table can be interpreted as a probability. 2, find the probability there will be no errors made. And 3, find the probability exactly one error is made. The first part, which is to show that this can be interpreted, this table can be interpreted as a probability, is about this property, these two properties here. First, all the probabilities are greater than or equal to 0, so there's no negative probabilities. And then second, if we sum all the probabilities, and also this is the discrete case we're looking at, if we sum all of these numbers, and I'll let you do that yourself, but if you add all of these numbers together, you will get 1. So it can be interpreted as a probability. So I have the summation written over here. And the two facts is that sums to 1 and all probabilities are greater than or equal to 0. The second part, find the probability there will be no errors made. So no errors means probability of x is 0 and y is 0, and that's just this value here, 0.84. Next is the probability that exactly one error is made, and that can either happen because there's what is x equal to defective weld, or there is exactly one improperly tightened bolt. And so that's just the sum of p of x is equal to 1, y is equal to 0, or p of x is equal to 0, y is equal to 1. So that's over here, x is equal to 1, y is equal to 0, 0.6. x is equal to 0 and y is equal to 1, 0.03, so we get 0.09 as our answer. And there's one more question for this problem. What is the probability there will be no improperly tightened bolts? And that's just the probability that x can equal anything and y is equal to 0. So here we have, the bolts are here. It's basically summing down this row against, you're going to sum up all values for x for y is equal to 0. So summing all the numbers, you should get 0.84 plus 0.06 plus 0.01, which is 0.091. So this idea here, when we want to talk about the behavior of y, is leading into marginal density. But essentially, if you want to know y is equal to something, you find the probability y is equal to whatever number you're looking for, and you sum over all possible values of x. Again, that's the idea of marginal density, just getting a little bit ahead. So the next example is a continuous distribution. In a healthy individual, aged 20 to 29 years, the calcium level in the blood, and the calcium level is our random variable x, is usually between 8.5 and 10.5 milligrams per deciliter, and the cholesterol level, so our cholesterol level is random variable y, is usually between 120 and 240 milligrams per deciliter. Assume for a healthy individual the random variable xy is uniformly distributed over the rectangle whose corners are 8.5 120, 8.4 240, 10.5 120, and 10.5 240. That is, assume the joint density is as follows. Here we have f of xy is equal to c, that's our density, and x ranges between 8.5 and 10.5, y ranges between 120 and 240. Find c so that f of xy is a density function. So to start finding c so that f of xy is a density function, we're going to use this fact over here, that when you integrate over all possible values in x and y, that should be equal to 1. And so here I have integrated for all my possible values of y and then all possible values of x. So technically I should be going from negative infinity to infinity, but outside these boundaries, the density function is equal to 0. So here I have my density function, c, dy dx equals 1. So then you can see the steps in integration, and then I get c is equal to 240. So now I'm ready to do my next problem, now that I have f of xy is equal to 1 over 240. Use the joint density to find the probability an individual's calcium is between 9 and 10 milligrams, and cholesterol is between 125 and 140. So I've set up my integral with my f of xy, dy dx. And so you can see that I've integrated with respect to y. So then I take out my constant, I have y, I evaluate at 140 minus 125, I get 15 dx, I take out my constant, integrate, and I get 15 over 240. That's the probability that calcium is between 9 and 10, and cholesterol is between 125 and 140. So I'm going to skip joint cumulative density for now and go on to marginal densities because I can use my last two examples to motivate the discussion. So we're going to go back to this automobile plant worked by robots where the robots would weld two joints, and the number of errors or problems with that, number of defective joints welded would be x, and then they would also tighten 3 bolts, and the number of improperly tightened bolts would be y, and these were our probabilities, our joint distribution. And then at some point we found the probability, here it is, that there will be no improperly tightened bolts. In other words, we were only concerned about y. We wanted to talk about y, and we weren't worried about x. X could equal anything. And so we went down this column and we summed up all the values for y. And that's exactly what a marginal density is. It's that from the joint density, you want to be able to talk about one variable or the other, one variable independent of the other. And the way we do that is we sum up over all possible values of the other variable. So if we're looking for the joint density of x, we sum over all values of y. If it's a continuous function, then we integrate over all values of y, just like we did here. So I've updated my table to have the marginal distribution density function of y. So I summed up over all values of x equals 0, 1, and 2 when y is equal to 0, and that's my probability y is equal to 0. I did the similar thing for 1, 2, and 3. Then to get my my marginal distribution for x, I let y vary between 0, 1, 2, and 3. For x equal to 0, I summed everything up, and I got the probability that x is equal to 0. I did the similar thing for x is equal to 1 and x is equal to 2. And then also just to double check, when I looked at all the possible values of x, which is 0, 1, and 2, when I add them up, it's equal to 1. When I look at all possible values of y, which is 0, 1, 2, and 3, they also sum, the probabilities also sum to 1. Now we'll go back to our continuous example to find marginal densities. This is the one where we were looking at the blood for calcium level and also for cholesterol level. So calcium level was x, cholesterol level was y, and we found that the joint distribution looked like this. F of xy is equal to 1 over 240. And we want to find the marginal density for x and for y. And this is a continuous variable, so we're going to integrate. So now to do my marginal density for x, I'm going to integrate over all possible values of y, which is 120 to 240. My function, my joint density function, dy. So I do my integration and I get 1/2. That's again my marginal density of x. My marginal density of y, I integrate over all values of x and I get 120. So now with both my joint density and my marginal density of y, I can answer the question, find the probability an individual has cholesterol between 150 and 200. So I can do this with my marginal density function, integrating between 150 and 200, marginal density function, and I get 512. I could have also done this using my joint distribution function here, and then I would have to integrate over the y range I'm interested in and over the x range I'm interested in. But you will get the same answer, and also essentially you already did this integration when you found the marginal. So the marginal distribution basically does this for you in general, and then you can, when you want only y, you can just plug in y. But I'll go ahead and do this using the joint distribution. And here I've done it using the joint density function. So I integrated with respect to y first, and then with respect to x, and I simplify, and it comes back to 5/12, which agrees using my marginal, which is good. So before we leave marginal distributions, we should talk about independence. And here we have that two variables, x and y, are independent if and only if the joint density is equal to the product of the two marginal densities. So we'll go back to our example of robots that are welding joints and tightening bolts. So we want to know if random variable x and y are independent variables, and if they are, then according to our formula here, no, where is it? Here. That our joint distribution, this table, should be the same as the product of these two. So in other words, if we look at f of 0, 0, which is equal to 0.84, that should be equal to the product of fx of 0 and the marginal distribution of y at 0. So fx at 0, that's where the value of x, that's the two joints, is equal to 0. So that's equal to 0.9 when we add up all possible values of y for x equals 0. F of y, that's when y is equal to 0 for all possible values of x, was 0.91. But we can see that f of 0, 0 is not equal to f of x 0, f of y 0. So x and y are not independent. Now if we consider our example where we're looking at blood to determine the levels of calcium and levels of cholesterol, we found the density, the marginal density of x, which was 1/2, and we found the marginal density of y, which was 120, and we have the joint cumulative distribution. So are x and y independent? So if I multiply the marginal distribution of x times the marginal distribution of y, that's 1/2 times 120, I get 1 over 240, which is equal to the joint density. Therefore, x and y are independent. Now that we've discussed marginal densities and independence, we should go back to talk about joint cumulative distribution. We'll start by reviewing an example with one dimension where we have one random variable x, and we'll look at the 3 coin flips where x counts the number of heads. So this is our sample space. These are the probabilities of 0 heads, 1 head, 2 heads, and this should be 3 heads. And then if you recall, cumulative distribution, which is a big F of x of 0, that's the probability x is less than or equal to 0. And there's one case, which is 1/8. F of 1 is the probability x is less than or equal to 1. So that's the probability x is equal to 0 and 1. Probability x is less than or equal to 2, that's probability x is equal to 0, 1, and 2. And if you remember, as you go up, you keep on accumulating all the probabilities from basically negative infinity up to your value of x. And then here's the graph of what it looks like. X is equal to 0 is at 1/8. The cumulative density at 1 is equal to 1/2, and at 2 is equal to 7/8, and by 3 it's equal to 1, and you flatten out at 1 from there. So again, it's 0, and then it jumps up, and I should probably put that in a different color. It's 0, and then it jumps up, and then it follows this line. Now we can look at the problem, find the probability x is greater than 1 and less than or equal to 3 using the CDF. So we can certainly use the density function, which is just the probability x is equal to 2 or x is equal to 3, which is 3/8 plus 1/8, which is 1/2. But we want to try using the CDF. So if we look at the cumulative density at 2, that's equal to all the probability less than or equal to 2, including 2. And again, I'm just using my definition over here. And now if I look at the cumulative density function at 3, that's the probability that x is less than or equal to 3. So if I subtract fx of 3 minus fx of 2, what I'm left with, and I'll put this in red, I have this, and I go up to here, and because I subtract 2, this is the open interval. I did the wrong number, so I actually wanted 1 to 3. So if I look at the CDF at 1, I have 1 and everything less. So now, let me do this red. If I subtract f of 1 from f of 3, I get everything, not including 1, because I subtracted off this point as well. Over here, I subtracted off this point as well, but I get everything including 3, which is exactly what I want here. So we want to do something similar for the cumulative distribution for this joint CDF. We want to be able to find the probability that x is between x1 and x2 and y is between y1 and y2. So here I have my plot of x1, x2, y1, y2, and here's my point x1, y1, here's my point x2, y2. And now we want to find the probability that x is between x1 and x2 and y is between y1 and y2. So what we really would like is this probability rectangle that I'm going to shade over here. So what I'm going to do is I'm going to start with the cumulative density of x2, y2, because that's going to give me this huge region, right, from negative infinity to x2, negative infinity to y2. And then from there, I'll kind of do the same thing that I did before, and I'll make some adjustments. So let me write this in red so we can keep track of this x2, y2. And that's going to be all of this region shaded here. The first adjustment I want to do is take out everything below the y1 region. And I'm sorry, my line isn't quite right. So here it is, everything in this region here. So in particular, I can subtract out f of x2, y1, and that, again, that will take out everything in blue, this region here. And now I want to take out everything from here to here, from x1, everything less than x1. So I'm going to subtract out this green region, which will be f of xy, x1, y2. And again, this region, f of x1, y2, it's everything less than or equal to x1 and everything less than or equal to y2. So again, that's that green region. And I need one more adjustment, but let's just see what we did. We wanted this yellow shaded region, so I started by taking all the red region, everything less than or equal to x2 and less than or equal to y2. So the red region had too much, so I took out this blue region to take out everything that was less than or equal to y1, and I also took out this green region, everything less than or equal to x1. But what you can see, so the red region minus the green region, so that's good. The red region minus the blue region, so that's good. But you see that I've subtracted out this region here, the region less than x1 and less than y1. I subtracted it out twice when I subtracted it out for the blue region and I subtracted it out for the green region. So for that reason, I need to add that region back in, and that's the x1, y1 region. So again, I had subtracted this out twice, and you can see that because it has the green and blue lines. You can also see that it's because it subtracted out because 1, it was less than y1, and then 2, it was less than x1. So I need to add it back in once. And hence, you can see I get my formula here that's listed. I have f of xy at x2, y2 minus f of xy at x2, y1 minus f of xy at y1, y2, and then I need to add back my f of xy, x1, y1. So for our example problem, we're going to look at this CDF, this joint CDF here. It's equal to 1 minus e to the minus alpha x times 1 minus e to the minus beta y for x and y greater than or equal to 0. And the CDF is equal to 0 everywhere else. So we want to find the probability that random variable x is between 1 and 2 and y is between 2 and 5. So the region we are after is in this black box here between 1 and 2 and 2 and 5. And we're going to start by considering the point 2, 5, and we're going to look at the joint CDF at 2, 5 using the formula here. So I plugged this into my formula, and that represents all of this probability here shaded in blue. But now to get my triangle right, I need to subtract everything over here where y is less than 2 and x is less than 2. So here I plugged in 2, 2, and again that represents this area here. Y is less than 2, x is less than 2. So I subtracted this off from my blue area. And then next I want to subtract off the area here. The area here where x is less than 1 and y is less than 5. So I have that plugged into my formula here. And again, that represents x is less than 1, y is less than 5. So I've subtracted this green shaded region from the blue area. So far from the blue area, I had the blue area, then I subtracted out the yellow region, I subtracted out the green region, so I almost have the black region, but as we said before, we've subtracted out this region twice. We subtracted it out with the yellow region and with the green region, so we need to add it back in. So here I have it in my formula, and again, that's adding this region back in. So I guess maybe I should go this way. So if you look at it, I had that region in the blue area, but then I subtracted it out with the yellow. I subtracted it out again with the red, so I need to add it back one more time. And that would give me, again, once everything's subtracted out, I am left with my the area I wanted, the black area here. And this is the answer. It's f of 2, 5 minus f of 2, 2 minus f of 1, 5 plus f of 1, 2. And you can see you can do this if you just kind of analyze the areas. You don't even have to memorize this formula. I mean, if you have it on a cheat sheet, that's kind of nice to be able to check it. But it's also very easy to figure out by drawing. And we should add one more formula, which is to find the marginal CDF. You, for x, you basically take y, you let y go to infinity, which is sort of analogous to the marginal densities where you consider all values of y. But in this case, you're going to let y approach infinity. So going back to our example, if we want to find the marginal PDF of x, we let y approach infinity, and we get 1 minus e to the alpha x, and this will approach 0, so that's 1 minus 0, and that's your marginal CDF. So our last topics is about expected value and covariance. So expected value is a lot like when you have one random variable, it's a weighted average. So if you have a function of two random variables, then you plug in your x and y into your function, and then you weigh it by the probability. So we'll do an example of that. And then for continuous, same sort of thing. You plug in your x and y into your function, and then you weigh it by your probabilities, and you go through all values of x and y. Covariance. So covariance here, and there's a formula for it. This is the formula that you'll be using, but this is the formula that gives you some insight into what's going on. But covariance tells you about how x and y are related. In particular, it tells you if large values of x tend to be associated with large values of y, and on the other end of the scale, and small values of x are associated with small values of y. And you do this kind of by comparing your values of x with the mean. This should be a mu, but I didn't have a mu, so I put a u. Mu of x and mu of y. And we'll talk about that too. And last, we'll talk about the Pearson coefficient, which is the covariance, but it's scaled. And so that's kind of nice, and we'll look at that as well. So for our example, we're going to go back to the robots that are welding joints and tightening bolts. So for the expected value of x, I'm going to look at all values of x and y, and I'm going to have x, that's just my function here, times my probability. So all x, that's x from 0 to 2, all y is 0 to 3, y is 0 to 3, and again, the expected value is the function, again, that's just x, times f of x, y. So when I start, I'm going to start with x equals 0, and then I'm going to loop through the y's. So starting with x equals 0 and the outer loop, I have, and then varying y from 0 to 3, I have 0 times f of x, y, 0, 0, 0 times f of x, y, 0, 1, 0 times f of x, y, 0, 2, plus 0 times f of x, y, 0, 3. Then I have x equals 1, so I'm going to loop through again with x equals 1, and y going from 0 to 3, f of x, 1, 0, 1, 1, 1, 2, and 1, 3, all times 1, because that's my function x equals 2. So 2 times 2, 0, 2, 1, 2, 2, 2, 3. And these are the numbers, and it works out to 0.12. So here I have x plus y written out, and again we're going to let x go from 0 to 2, y go to 0 to 3, the function here, x plus y, times the probability. So again, I'm going to start with the outer loop being x equals 0, and I'm going to do the inner loop. Y goes from 0 to 3, so I have 0, 0, and x is 0 in all of these, and then y is going from 0 to 1 to 2 to 3. So I have 0 plus 0, that's my function, and then I have my f of x, y, the probability of 0, 0. Then I have 0 plus 1, that's my function, and then the probability that we have x equal to 0, y equals to 1. 0 plus 2, that's my function, the probability that we have 0, 2, 0 plus 3, and the probability of 0, 3. Then we look at x equals 1. So we have 1, 0 probability that x is 1, y is equal to 0. 1 plus 1, that's the probability, times the probability x equals 1, y equals 1, etc. And you can look through. So essentially what you're doing is you're looking at every possibility, every xy possibility. You're plugging in the x and y's into the function, and then you're multiplying times the probability. So the last one we have is the expected value of xy. So again, x goes from 0 to 2, y goes from 0 to 3, xy. Again, that's the function we have, the h of x function. And then the probability. So again, we're taking all combinations of x and y. We're multiplying it times the function times the probability of that x and y combination. So we'll start with x equals 0. We'll go from y equals 0 to 3. This is the line we have. This is x equals 1, x equals 2. And now notice the function out here. Everything on the top line is 0 since there's a multiplication. That's these, and then there's a 0. And then the first interesting one is we get 1 times 1 for f of 1, 1, f of 1, 1. We get 1 times 2 for f of 1, 2. So we have the 1 times 2 times f of 1, 2. And then we have 1 times 3 times f of 1, 3. The next line for x equals 2, we have a 0. We have 2 times 1 times f of 2, 1. Oops, maybe I did this wrong. X is 2, y is equal, oh no I didn't, y is equal to 1. We have 2 times 2, which is 4, times f of 2, 2. And then we have 2 times 3, which is 6, and f of 2, 3. And when we add it together, that's our final expected value. So that's the expected value of x times y. And again, we get that by multiplying every combination of x times y, and then multiplying the product by the probability. So we've calculated the expected value of x, we've calculated the expected value of xy, and I'm going to give you the expected value of y so that we can calculate the covariance of xy. We'll talk about the meaning of covariance later. So I'm going to use my formula over here. So it's a pretty quick plug it in, and this is the covariance. Going back to my example with the blood calcium level and cholesterol level, where this is my joint density, I can find the expected value of x times y. So the expected value is just the integral over all possible, so we want to go over all possible values of x and y, the function x times y times the probability of these x and y's. So we integrate x from 8.5 to 10.5, y from 120 to 240. Again, we have the function xy times the distribution, the joint density times dy dx. And so then I do my integration with respect to y, with respect to x, and I get 1710. So we have calculated e to the xy here. I'm going to give you e to the x and e to the y's. So then we can plug in to the covariance formula, and we get 0. So really what we need to talk about is what the significance of covariance. And for that, we're going to look at this part of the formula. So actually the definition of covariance is the expected value of the distance of of your x from the mean of x times the distance of your variable y from the mean of y. So we'll look at what that means. So here I have my plot of x and y with the mean of x here, the mean of y here. And what we want to know is, do relatively large values of x correspond with relatively large values of y? Or is it the other way around, where large values of x correspond with small values of y? And when I say relatively large values, I'm talking about comparing values of x with the mean of x. So here, the values that are larger than the mean, do they correspond with values of y that are larger? Hence, you'll see you have in this formula, you're looking at x minus the mean and y minus the mean. So let's look and see what happens with that product. So if you have values of x that are larger than the mean, and they are associated with values of y that are larger than the mean, then your x minus the mean is going to be positive, and your y minus the mean is going to be positive, and this product here is going to be positive. So I have that summarized here. Large values of x corresponds with large value of y, means that this product is going to be positive. And then we should also consider, what if you have a value of x that's smaller than the mean? How does that compare with values of y? So if they compare with smaller values of y, and again we're saying relative to the mean, then x minus the mean is going to be negative, but y minus the mean is also going to be negative, so your product will be positive. Now we can compare that if we have large values of x, relatively larger than the mean, associated with smaller values of y. So we're going to have x minus the mean is going to be positive, but this is going to be negative. So I have that summarized here. And now if we go on and say, then small values of x correspond with large values of y, if we look at our product, this here is going to be negative, x minus the mean. But this over here, the y minus the mean, because now y is larger, relatively larger, is going to be positive. So the product, again, is going to be negative. So what we have is the covariance tells us about how x and y are related. If covariance is positive, that means large values of x are associated with large values of y, and correspondingly small values of x are associated with small values of y. If covariance is negative, that tells us the opposite is true. Large values of x are associated with small values of y, and small values of x are associated with large values of y. So again, the sign of the covariance tells you how x and y are related. Then the last thing we have is this Pearson coefficient of correlation. So it's basically the covariance, but we normalize it so that all of these coefficients, these Pearson coefficients, are between -1 and 1. So writing this down, again, the Pearson coefficient normalizes the covariance, so values are between -1 and 1, and that's why it's divided by var x and var y. That's the normalization. And then the measure is a measure of linear relationship. So when you talk about are x and y correlated, this measure, or these measures, are about linear correlation. And if there's no linear relationship, that doesn't mean that they're not related. Like the covariance, a positive coefficient means the line slopes up. In other words, positive or larger x are associated with larger y, and smaller x are associated with smaller y. If the Pearson coefficient is negative, that means the line slopes down. So larger values of x are associated with smaller values of y. Again, it's the same thing as covariance. The closer, again, the values range between -1 and 1. The closer to 0 means there's no linear relationship. And the closer to 1 or -1 means a high linear relationship. So here I have some scatter plots for you. This is where the correlation coefficient is near 0, and you can see it's just kind of random. As we get closer to a +1, we get more and more close to a line, and because it's positive, everything tends to slope up. Here we have the negative. As we get closer to -1, we get closer and closer to a line, and because these are all negative, we have this downward slope. And again, a 0 correlation coefficient means there's no linear relationship, and in these drawings it looks like there's no relationship at all, but that's not always necessarily the case. So for example, something like this clearly doesn't have a linear relationship, but it doesn't mean that there's no relationship between x and y, because obviously there is. It's a parabola. So again, these coefficients measure linear relationships. Okay, that's it for the review. Thank you for watching.